Yeah, so I'll talk about bridging pandas and polars, the two most commonly used data frame formats, and the hidden costs of data frame interoperability. And I'm Ivo Dilov, a software engineer at ArcticDB, which is one platform that has faced these challenges. So yeah, the agenda for today is to cover what data frame interoperability actually means, and why is it important, and we'll cover many of the differences between pandas and polars memory layouts, the sparse data differences between the two, the schema differences, and how should we handle pandas indices in polars. So yeah, let's start with data frame interoperability. So for a system to be interoperable between data frame formats, we want that to be relatively seamless, so without much code changes, to be able to work with both pandas and polars formats. We want it to work reliably, so every data frame can be represented in both formats, and we especially want to be performant, so to be efficient in terms of both time and memory. In the context of a data frame database, this means that we should be able to store data frames in both formats. We should be able to modify existing data frames in both formats, and we should be able to read them out in both formats. So, for example, a data frame database should allow writing a polars data frame to storage, appending a pandas data frame to that, and reading the result as either polars or pandas. I will cover this talk through the lens of ArcticDB, which is a high-performance data frame database. It's time series focused. It's developed at Man Group for its quantitative research use cases. And it's open source on GitHub, although worth noting that latest versions are under BSL. It was initially designed with a pandas-only interface. The polars interface appeared later, and we'll go through some of the challenges to adding this interoperability in this talk. And yeah, it's worth noting that on storage, ArcticDB uses a custom format, which is neither pandas nor polars. And yeah, it hasn't changed during the migration. The migration is only just attaching a polars interface to the existing system. So why does data frame interoperability matter? Probably some of you have worked in large organizations and have noticed that different teams prefer to do things differently sometimes. It's very frequent, for example, for a hedge fund manager to have different systems talk to each other, but fundamentally be written in different, using different libraries. So we could have something like market data gathering platform, which is using polars. This then feeds into an alpha prediction model, which is based on pandas and scikit-learn. And then when we go to the trade execution itself, it can be actually based on Rust, but using Arrow memory format, which is what polars is actually based on. Data frame interoperability is important because it will allow mixing those different platforms together in an efficient way. Another reason why interoperability is important, even if you use the same format throughout all of your systems, is that eventually you might want to upgrade your formats. So many companies are currently upgrading from pandas to polars because of the performance benefits. And if you have good solution for data frame interoperability, it will allow you to migrate different systems one by one instead of moving them all in one big bang upgrade. So let's start talking differences between pandas and polars. So we'll start with the memory layout differences. Pandas data frames have many different possible memory formats. I'll talk mostly about the most commonly used one, which is just the sequence of NumPy buffers. So essentially, each data frame can be represented as a sequence of columns. Each column is a continuous block of memory from the same data type. So in this example, column A is full of integers. They're all in continuous memory. Column B is in another continuous memory block, and so on. As mentioned, Pandas allows different memory layouts. So for example, if all your columns are actually from the same data type, you can consolidate them together and actually have all of the columns in a single continuous buffer represented as a two-dimensional NumPy array. As for polars, its data frames are based on the Arrow memory layout, which was briefly discussed in previous talks as well. But Arrow memory layout essentially allows each data frame to be represented into multiple record batches, which are essentially row slices. So for example, we could have one record batch, which is rows, the first 1,000 rows, then have another record batch, which is for the second 1,000 rows. And each record batch has its own columns in continuous memory. But this essentially means that we could have one column for the entire data frame, for example, column A, to be split into multiple different continuous memory blocks. It's worth noting that most commonly, if you use polars, it will prefer all of the data to be in a single record batch. But it depends, for example, if you're using streaming data, then it's more probable to be more fragmented in terms of memory. Another big difference in the memory layout is how the two systems handle strings. In particular, the NumPy string format and the Arrow string format. It's worth noting that Pandas before version 3.0, the default way to handle strings was to use the NumPy string arrays, which I'll cover here. So the way we handle string columns is to just have what we call an object data type NumPy buffer, which is essentially just a continuous memory buffer which holds pointers to Python objects. And these Python objects are allocated by Python on the heap. And for strings, they are just columns. There's just strings in Python. So if we have the column containing hello world exclamation mark, this will have 3 different Python strings allocated by Python and pointers pointing to them in the NumPy buffer. Important to note here is that constructing such a NumPy buffer requires actually acquiring the GIL for each string allocation, which essentially means we can't do all the allocations in parallel because of the global interpreter lock. The other more modern way to store strings is the Arrow format. So Pandas 3.0 and later by default uses the Arrow format, but it's still, in terms of interoperability, you might have different systems speaking different Pandas versions. So it's important to be interoperable between the two. And yeah, how are Arrow strings represented? Main benefit with Arrow strings is they don't actually require allocating Python objects. They're just natively represented in the Arrow memory layout. So if we have the same input of hello world exclamation mark, the way this works is we concatenate all of the strings together into a single data buffer, which you can see below. And we have a separate offsets buffer, which points into the data buffer. So in the offsets buffer, we hold the starting position of each particular string. So if we want to read the second string world, we look at the second element at index 1 in the offset buffer, which is 5. So we can start reading from 5. And when do we stop reading? When we stop reading when we reach 10, which is the place where the next string starts. And yeah, an important note there is that since we need to know the end of the last string as well, the number of offsets are actually 1 element more than the number of strings in the buffer. So since we have so many differences between the memory layouts, between Pandas and Polars, converting between the two can obviously be expensive. The simplest case in which we have the memory layouts actually match is continuous numeric buffers. So if we have one continuous memory block of ints and one continuous memory block of ints both in Polars and in Pandas, we can actually cheaply convert between the two. We can just move the pointer from one to the other and end up with shared ownership between Pandas and Polars. But by default, this doesn't happen. Like if you, for example, want to convert a Pandas data frame to Polars by using Polars from Pandas, this will, even if the memory layout matches, it will do a memory copy. This is actually a good thing in most cases because shared memory ownership can be confusing to users. It's much easier to explain what happens if you are the sole owner of the memory. But it's possible to do the conversion more quickly. For example, if we go through the Apache Arrow package as an intermediary. Where we cannot avoid CPU cost and memory copies is, for example, if we have multiple record batches in the Polars or Arrow frame. In this way, the array might be separated into multiple chunks, what we call a chunked array. And if we want to convert it to a NumPy buffer, we essentially need to allocate one continuous buffer to place all of the data in it, and memory copy each chunk one by one into that. Still, that's fairly efficient. It's just a memory copy, and even more, we can do the different memory copies in parallel because they touch different memory. The more expensive bit is actually how we handle string columns. If you want to convert a Pandas 2.0 to a Pandas 3.0 or Pandas 2.0 to a Polars data frame, we have to handle all of the differences discussed before, and in particular we have to allocate or deallocate the Python strings which require getting the global interpreter lock, which means we can't really do that in parallel. We have to do them one by one. So, how do we solve the problem of integration? Any system that needs to work natively with both formats essentially has to make a choice. We either use one of the interfaces, either Arrow or NumPy by default, and if users need to work in the other format, we essentially pay the conversion costs. So if we had a system written solely in Arrow, but we had users that want to use Pandas, they will have to pay the conversion cost between the two. What we have done in ArcticDB is a bit different. We have made two different interfaces, both to Arrow and to NumPy, which work natively and directly translate into the internal storage layout of ArcticDB. So you can write a Pandas data frame into ArcticDB, and the ArcticDB engine will natively understand the memory layout of the Pandas data frame and efficiently encode it into the storage layer. And it can do the same with the Polars data frame. And on the read side, we can decode what we read from storage directly into Pandas memory layout or into Polars memory layout. So with this double integration, we can actually achieve good performance in both cases. So let's talk some benchmarks. If we're discussing the numeric case, which is a bit simpler, for all of the benchmarks you see on the right, we have used 10 million rows by 100 columns random floats data frame. And you can see the conversion costs between converting Polars and Pandas via memory copy, like with the native Polars methods from Pandas or to Pandas. It actually takes around 250 to 300 milliseconds to do that conversion. This can be, in some use cases, this can be quite expensive, especially if you compare just to regular reads from storage. In terms of read operations, I have compared ArcticDB, which is the project I'm working on, to the most commonly used storage format for data frames, which is Parquet, which is Arrow-based. So if we read from local disk, from Parquet to Pandas, it is actually quite slow. It takes around 3 seconds. That's because Parquet is not really optimized for Pandas. It's optimized for Arrow. And as you can see, reading into polars is actually quite fast, around 300 milliseconds. And ArcticDB, with its both integration into Pandas and polars, can actually read the result relatively quickly, around 250 milliseconds, into both memory formats. Initially, with ArcticDB, we had only the Pandas integration, and if we had done the naive conversion approach, i.e. read into Pandas, then convert to polars, it would have actually resulted in around 500 milliseconds of read time, which, as you can see, is around 2 times slower than what we actually get. About the string data frames, which are a bit more interesting. Here we have benchmarked Pandas 2.0 to a polars conversion. In this case, I've chosen a data frame which is roughly of the same size as in terms of memory usage, because strings are larger. So I've used a 1 million row data frame with 100 columns, and converting between the two, between polars and Pandas, then becomes multiple seconds. It can take up to 5-8 seconds to do the conversion, essentially because you have to allocate or deallocate the Python strings from that. And yeah, in terms of read operations, if we read either from local disk, from Parquet or ArcticDB, it is still quite expensive to read into Pandas because we have to allocate all of those strings for the NumPy buffers. So it takes 5 seconds for Parquet or 3 seconds and a half for ArcticDB. And here we can see one of the big differences and important reasons why Arrow is becoming more important. Strings are much better handled. Reading both from Parquet or ArcticDB is less than a second, less than half a second actually. And yeah, if we had, in this case, if in ArcticDB we had implemented the polars reads as reading into Pandas and then converting, it would have actually taken around 10 seconds, which is very slower than what we currently have at around 500 milliseconds. So that's it for the memory layout, and we can talk a bit about how sparse data is handled differently between the two frequently used memory layouts. So in Pandas, with NumPy buffers, the de facto way to handle sparse data is with what are called no value sentinels. So for example, if we have a float column, we would just put nuns inside the float column, or if you have a timestamp column, you put NATs, not a time, in the timestamp column. And these special byte values represent missing values. There are other ways Pandas can handle missing values, for example, sparse arrays, but they have a different memory layout and have other performance repercussions. And as previously mentioned, newer versions of Pandas can actually use Arrow memory layout, which has a different way to handle sparse data. So how does polars do sparse data? Well, as mentioned, polars relies on the Arrow specification of memory layout, and Arrow has a native representation of sparse data. So if we have missing values, we represent that with what is called the validity buffer. So we can have ones or zeros, depending on whether the value is present or missing. And this essentially means that where we have a 0 in the validity buffer, this means that this value in the data buffer is missing, and it doesn't really matter what bytes are written there. It can be any bytes as long as they're of the right size. So how do we integrate the different sparse data? So in terms of conversion costs, NumPy to Arrow or Arrow to NumPy, it's essentially a different memory layout, and we can't really avoid doing a linear scan to find where the no-value sentinels are, or to find where the validity bitmap is set to 0, and assign no-value sentinels or assign values to the validity bitmap buffer. So there is a conversion cost similar into the memory layout. What ArcticDB does for this is as previously mentioned, it has integrations with both formats, so it natively either directly populates the validity buffer or directly populates the no-value sentinels to do that efficiently. The more interesting question is what we do about sparse integers. Because, as mentioned, Polars uses no-value sentinels to represent missing values, but there is no-value sentinel for int columns. Each byte value for integers is a valid integer value. So we are essentially left with a choice. If we want to represent a Polars data frame with missing int columns, how do we do that in Pandas? Well, there is no ideal solution. What ArcticDB does, and what Pandas does with a lot of its own operations itself, is to just represent the no's as zeros, which is fast, because it's essentially the same as doing a no sentinel, just labeling 0 as the no sentinel. But this loses information. If we had a 0 or a missing value, we wouldn't be able to differentiate the two. Another option is to convert floats, to convert the ints to floats and use nonce. This requires a bit more performance cost because we need to cast each integer into the float in the first place. So we have one more O of n CPU cost. But also it loses some precision. As you probably know, if we have a 64-bit float, this means we have only 56 bits for the mantissa, which can actually represent the integer precisely. So if we have integers larger than 2 to the 56, they will actually get rounded to, let's say, a value divisible by 2 or divisible by 4, etc. Another option is the previously mentioned sparse arrays. But they have many performance implications. Namely, they don't support random access. Like you can't get the 5th element of the sparse array very quickly. Yeah, it's an option, but it's not ideal in terms of performance. So let's talk about some schema differences. And more particularly in column names. So Pandas schemas are actually fairly relaxed. They do allow duplicate column names. You can have a Pandas data frame which has only the same column name, which is quite absurd, but it's allowed. It also allows strings, integers, any other types to be the column name. Whereas Arrow schemas are quite strict. They do not allow duplicate columns. Each column name is a string only. And this leaves us with some questions on how to convert the invalid Pandas data frames into Polars. So what we do about the non-string column names? Well, it's pretty obvious. We can just convert them to strings. For example, the integer one, we convert to the string one and use that as the column name in Polars. This can result in some duplicate column names. Like if we had the different column names, the string one and the integer one, that would become to 2 different string one representations. So we do have to handle duplicate column names. For duplicate column names, standard conversion methods just throw an exception because it's essentially correct. This is an exceptional situation. It's not representable by the Polars memory layout. But ArcticDB has petabytes of Pandas data frames stored inside it. We can't really afford our researchers to lose access to some of their data if they want to convert to Polars because they have used some invalid Arrow schema. So ArcticDB has to solve the duplication problem. And obviously, there's no ideal way to deduplicate columns. What ArcticDB does, it just adds underscores until it achieves full deduplication. So for example, 1 and 1 will become to 1 and 1 with underscores. Renaming columns is not ideal. We need to somehow preserve the original columns, what they were. So there is a piece in the Arrow schema which allows us to store metadata, and that's essentially where we store just some JSON metadata about the column, which allows us to return it back to Pandas if it's needed. So it has the original name, which is just the one integer, and the new field name, which is the one we see in the Arrow table. And just, a quick example. In ArcticDB, you can do the following. You can create a data frame which has 3 columns named 1, 2 columns named col. And if we read it back as polars, we will actually get something that looks like the result on the right. We will have underscores deduplicating, and we will have the integer 1 be converted to a string 1. And we will have the additional metadata in the polars data frame if we need to extract that. So there are other Pandas metadata we want to care about, and the big elephant in the room is Pandas indices. So Pandas data frame can have the concept of an index. What does that mean? So the index is essentially a special way to quickly access a particular row. So for example, you can find the row which has a particular timestamp if your timestamp column is the index. There are different types of Pandas indices. The most commonly used one by default is the range index, which is just a numbering from 0 up until the size of the data frame. So you have like 0, 1, 2, up until n-1. This is not actually represented in memory as a separate column. It's just represented like a piece of metadata. It just stores the start, the stop, and the step, similar to a Python range function. The most common use case, in particular for ArcticDB, is time series indices, which is just one column which has the special property of being an index. It can be of many types. In ArcticDB's use case, the most commonly used one is the datetime index. And it has additional metadata alongside it, like whether the index is sorted in ascending, descending where, or it's unsorted. There's also multi-index, where we can have multiple index columns. This is essentially similar to having one index, one column, but multiple, so we can find the column which has these 3 values for these 3 columns fairly quickly. It's important to note for multi-index, the memory layout is actually different. It doesn't use the columnar memory layout. It uses a more optimized format for quickly finding that particular row. So how do we represent such Pandas indices in polars? As mentioned before, ArcticDB has petabytes of Pandas data frames written inside it. We must have a reasonable representation when we read back those into polars. Well, range indices, they can be represented as plain metadata added to the same Arrow schema metadata, so they're not that interesting. And the most common use cases, at least for ArcticDB, is the single column index. We can just represent it as a regular column. We just put it as the first column of the polars data frame. We preserve the name of the index column, and if it's missing, we just use the basic index name, because empty column names are not allowed in Arrow schema as well. And we should preserve any index metadata that we had. For example, if the index was sorted, we actually want to tell polars, okay, this column is sorted, so polars can be more efficient when it does processing, like it can use binary search or more efficient group bys, knowing that the column is sorted. For multi-index, we just attach the multiple columns up in the front of the polars data frame. But yeah, it's worth noting that this actually requires some memory layout changes, so it's not exactly the same data structure, but it's the Arrow equivalent of that. It just stores them as regular columns in polars. So what do we do in the other direction? If someone is writing to the database a polars data frame, how do we interpret that? Does it have an index? Does it not have an index? Well, essentially for the indices, it's a user-defined property. You can't really say if a polars data frame should or should not have an index. It's something that only the user can specify. If they want to have an index, they can specify that with an appropriate API. Or if they don't care about indices at all, that should also be fine. We can default to the default range index used by Pandas. Yeah, and in ArcticDB in particular, this is very important if we have time series column in the polars data frame. We want to be able to index according to that, to have ArcticDB optimized operations on that time series index. So let me go through a quick example. The font is probably a bit small for the actual code example, but essentially we can write 100 million row polars data frame. You can see on the left part of the example, we have a data frame which has 100 million rows, and the first column is a timestamp column. And when we write it into ArcticDB, where we store it in the library, we write the data frame, and we just specify use the first index as the column. Use the first column as the index. Then, when we read that back into Pandas, we will essentially represent the timestamp column as the index column. And more importantly, once we know that the first column can be used as an index, we can do more efficient operations on it. For example, in this code stub I have used here, we just want to get the date range from the 6th of June to the 7th of June. And we can read that out in just 1 millisecond, which is quite fast for 100 million rows. If we had to actually read the entire data frame, it would have taken more like 500 milliseconds. So yeah, this shows how ArcticDB can leverage the index for more optimized performance with the time series column. So to wrap it up, some takeaways from this talk are that conversion between polars and pandas formats can be surprisingly expensive in some cases, especially if we're talking about pandas 2 and string columns. If you want your system to have good performance with both, you essentially have to have native integration with both formats. For a database like ArcticDB, it needs to have a way to decode the storage directly into either pandas format or polars format, and it has to do that efficiently. Sparse data is represented differently. There are especially some trade-offs in how we should represent missing int columns with pandas. No ideal solutions there, all come with trade-offs. Schemas can be incompatible. To translate between the two, we need some form of metadata and a translation layer. And pandas index handling in polars requires some custom APIs for the users to specify their indices, or meaningful representation of those indices when users want to read back polars.
That is a speech 15.
Yeah, thank you.